a dot and a cross. So, do you know the symbol of this dot and cross? What is it? Dot means towards you, right? Towards you. Cross means going inside, right? If this conductor current is entering, right? Current is entering. So when you see the conductor is like this, that is towards you. And another conductor cross section, if this area is A. It means it's entering. Current is entering to in the board. Okay, and sorry, it means, and this one is the cross. Cross is in magnetic circuits. You have done it in the first year. This one is the inside. Cross is inside, exactly. Cross is inside, and this one is towards me. That is outwards. So when a conductor it carries a current, what happens? It encircles. We can experience a magnetic field M, and the electric field is going outwards. When we will read electric field theory, and that time you will understand. Electric field is denoted as E, magnetic field is denoted as H. Now, today we will learn coupled circuit. See, in your syllabus, what is there? The coupled circuit, magnetic coupling, polarity of coils, polarity of induced voltage, concept of self and mutual inductance, coefficient of coupling, modeling of coupled circuit, solution of problems. These are the syllabus. So what is a coupled circuit? When two or more circuits, often in the form of multi-turn coils, sharing a magnetic circuit. Now, what is a magnetic circuit? I will explain you, don't worry. Where the magnetic flux produced by the current in one coil not only links with its own windings, but also with those with other coils. You just try to remember the circuit of transformer, the schematics. Simple, that is ideal transformer. This is load. This is coil 1 of inductance L1. This is coil 2 of inductance L2. The I1 current is entering. And when in transformer, when the winding which is connected to the source, we call it primary winding, right? And when current I starts flowing, what happens? EMF is induced in the primary winding. This EMF we write as E or capital E. Now in transfer we know that E1 by E2 is equal to N1 by N2 is equal to I2 by I1 is equal to A transformation ratio. Actually, and this is V1 by V2. What is V1? V1 is the source voltage. What is E1 is the EMF induced in the primary winding. What is V2? V2 is the load voltage. That is, we are getting the output voltage from the transformer. So, a transformer, there is no electrical connection between in transformer. There is no electrical connection between the primary and secondary. What happens? As current starts flowing in the primary, the flux links the secondary winding. And we know that the EMF induced in the primary winding, this E1 is equal to minus N d phi 1 dt. That is EMF induced due to rate of change of flux. And this N1 means number of turn in the primary winding. So coupled circuit is basically already you know it from the transformer chapter in first year, first semester. Now, in second year syllabus, we must know what is a coupled circuit. So when two or more coils are very close to each other, then current in one coil will affect the EMF induced in other coil, and these coils are said one or more coils, right? So it should be plural, are said to be mutually coupled or magnetically coupled circuit. So what I have written, when two or more coils are very close to each other, then current in one coil will affect the EMF induced in the other coil. And these coils are said to be mutually coupled or magnetically coupled. So in any coil, so this one is coil 1 and current is passing through its I1T, instantaneous current, and this is the inductance L1, and this is another coil. Check I1T is passing through this coil, and this inductance is L2. So we can see the effect of I1T in the coil 2. Similarly, effect of I2T, if there is a change in I2T, we can see the effect in this coil also. I'll draw it in a big way. So the voltage is V1, current is I1, inductance is L1, and another coil. Here the voltage is V2, current is I2, inductance is L2. So here we can see two coils with inductors L1 and L2 are placed close together. Let the currents coil I1 and coil I1T and I2T. I1T means instantaneous current. I1T, I2T is equal to instantaneous current. Instantaneous current. The current I1T in coil 1 produces flux Phi1. The I1T in coil 1 produces flux Phi1. So I1 Phi1 is equal to flux produces by I1T in coil 1. Now part of which link coil 1 is the part of which means Phi1, part of which link coil 1 and remaining flux link coil 2. Let the flux linking coil 1 is denoted as phi 1 1, and the flux linking coil 2 is phi 2 1. That is, this phi 2 1 so here we can see the flux. One is phi 1, this flux linking to the coil 1 is phi 1 1, and flux linking to the coil 2 is for this current is phi 2 1. So this one is the phi 2 1. Phi 2 1. So one is this phi 1 is equal to flux produced by current I1. Some part of it linking coil 1 and some part is linking coil 2. So this flux is, then we can write phi 1 is equal to phi 1 1 plus phi 1 2. Similarly, the current I2 produces flux phi 2 part of which means that is phi 2 2 link coil 2 and remaining flux phi 1 2 link coil 1. Then phi 2, that is flux produced by I2, is equal to phi 1 2 plus phi 2 2. That is, this flux is due to current I2 that links the coil 1. This is for coil 1 and this is for coil 2. So in mutual inductance means these two coils are placed very close to each other, and current of coil 1 is affecting the EMF induced in coil 2. Similarly, current in coil 2 is affecting the EMF induced in coil 1.
And phi 2 will be equal to 5 2 1 plus 2 2 or 1 2 plus 2 2.
Yes. We can write this way also. Initially, we have written phi 1 as phi 1 1 plus phi 1 2. That is, this flux is flux is produced by current I1 and it's linking coil 2. Right? Now, this flux is produced by current I2. Even I can write, if I write this one as phi 2 2, that is flux linking to coil 2 plus flux linking to the coil 1 due to the current I2. Here, just I have written no, phi 1 2 as first. Basically, this one is a part of phi 2, flux produced by the current I2 in the second coil. When second coil, what we can see the flux produced by this current I2 is I'm drawing as red. This one is the red. Now this flux linking to this coil is phi 2 2. Now this total flux is phi, and part of this flux is linking to coil 1, which is phi 1 2. Clear? Now, EMF induced in coil 1 due to its own flux. The EMF induced in coil 1 is due to its own flux phi 1 1 and the flux phi 1 2, that is due to the current I2. Therefore, we can write the total flux linking coil 1 is phi L1 is equal to phi 1 1 plus phi 1 2. This is, that is, if you see the diagram again, I am drawing the diagram here. Better for you. This is one coil, current is I1. And flux linking to this coil due to this I1 and I2. One is black, another one is red. So one is total flux linking to coil 1 is one for its own. That is for this one, phi 1 1 first one. And second one is for the second current, I2, which is denoted as red color. Next, the net flux linkage. The net flux linkage of coil 1 is, say, lambda 1 is equal to N1 number of turns into number of flux linking to it. So N1 by N1. So this is equal to N1 by 1 plus N1 by 1 2. This is the flux linkage. Now flux linkage N1 by 1 is due to the coil 1 own current. I1. So the flux linkage N1 by 1 is due to the coil's own current I1. That is coil 1's own current. And in the coil 1 current is flowing I1. This current is I1. Therefore, N1 phi 1 is equal to L1 I1, where L1 is called self-inductance of coil 1. Self-inductance of coil 1. Now the second term what is the second term? N1 phi 1 2. Second term N1 phi 1 2 is produced by the current in coil 2, that is N1 phi 1 2 is equal to plus minus M12 I2. For you, M12 I2, M12 is mutual inductance of coil 2 due to the current I2. M12 is a mutual inductance. So M12 is the mutual inductance. The reason for plus minus M12 is that the flux component phi12 is due to the current I2 may be in the same or opposite direction as that produced by coil itself. Now, by Faraday's law of electromagnetic induction, V1, the voltage of coil 1 is equal to d lambda 1 dt is equal to ddt of N1 by L1. Now, phi L1 is, we know that this one is N1 phi 11 plus N1 phi 12. So, this is equal to ddt of L1 I1 plus minus M12 I2. So this is equal to L1 d I1 dt plus minus M12 d I2 dt. Similarly, for coil 2, lambda 2 into flux linkage lambda 2 is equal to N2 phi L2. This is equal to N2 phi 22 plus N2 phi 21. So we have N2 phi 22 is equal to L2 d I2 dt. That is basically what is it? L2 d I2 dt. That means, any idea? N2 phi 21 is equal to plus minus M21 mutual inductance, na? M21 I1, where L2 is the self-inductance of coil 2 and M21 is mutual inductance. Two coefficients of mutual inductance are not necessary. We consider M12 is equal to M21 is equal to M. Then we can write V2 is equal to voltage of coil 2, right? V2 is equal to d lambda 2 dt, rate of change of flux linkage, as this is equal to ddt of N2 phi N2 phi L2 phi L2 means flux produced by the inductance L2. So this one is equal to ddt of for N2 phi 22 plus N2 phi 21. Or we can write this is equal to ddt of L2 I2 plus minus just as previous one M I2. So this will be L2 di2 dt plus minus M this will be I1 because mutual inductance due to the current I1. We are considering the second coil. So M di1 dt. So V1 I can write this L1 di1 dt plus minus M di2 dt and V2 is equal to plus minus M di1 dt plus A2 di2 dt. So what is V1? V1 is the voltage of coil 1. Let's see the figure again. This is the coil 1 and this is the coil 2. So this is the voltage of coil 1, not EMF induced. I1 current is entering. This is L1. This voltage, the sum of this EMF induced of this coil 1 and the mutual inductance due to this coil 2. This mutual inductance is denoted as M. So I can write this V1 is equal to L1 di1 dt, that is EMF induced due to this current I1 in coil 1 plus the mutual inductance produced by this current I2, the M plus minus M di2 dt. Similarly, voltage of the second coil, this will be the first mutual inductance of coil due to current I1 plus self-induced EMF, that is L2 I2 dt. This is part for mutual inductance and this is for the self-induced EMF. The mutually induced EMF, this voltage is sum of, this voltage must be sum of these two voltages. Similarly, this voltage must be sum of two voltages. This voltage is sum of the self-induced EMF, this voltage plus due to the mutually induced EMF plus mutually induced EMF. In the second coil, current is I2. So the EMF induced due to this current I2 to this coil. So this voltage V1 will be L1 di1 dt plus minus M di2 dt. Similarly, this voltage V2 is equal to plus minus M di1 dt plus L2 into di2 dt. This is a self-induced. This is self-induced EMF. Next, we learn the dot convention. Dot convention. So in many circuits, you can see the figure like this. This is one coil. This is another coil. And in between, you can see there is mutual inductance M. So this current is I1 and this current is the I2. So this voltage is V1 and this voltage is V2. And we know the voltage of V1 and V2, the expression already. We have done it. You see there is some dot. The current entering. And second coil also current entering, dot is here. So what is dot convention? In the circuit analysis, the dot convention is a convention used to denote the voltage polarity or the mutual inductance. So dot convention is the convention used to denote the voltage polarity of the mutual inductance. So if a current enters the dotted terminal of one coil, that is, if the current enters the dotted terminal of one coil, then the polarity of the EMF induced in other coil will be positive at the dotted terminal of the second coil. So that means if the current enters the dotted terminal of one coil, then the polarity induced in the other coil will be positive at the dotted terminal of the second coil. And second one is, if a current leaves the dotted terminal, say another coil, if the current leaves the dotted terminal, if the current leaves at the dotted terminal of one coil, then the polarity of the EMF induced in the second coil will be negative at the dotted terminal of the second coil. But we can write that I'm writing the simple way, dot convention. If two currents are entering or within bracket leaving into the dot at the same time then voltage generated due to mutual inductance will be positive. If two currents are entering or leaving into the dot at the same time, then the voltage generated due to the mutual inductance will be positive. You see this too? In both cases, this one is current is entering at the dot and current is leaving at the dot. So in that case, mutual inductance will be positive. this is 1 and this is 2. This 2 convention is very, very important. If one current is entering, with an or leaving the dot, and another current is leaving, within bracket, entering the dot, the voltage generated due to mutual inductance will be negative. Let us say one is, with first one we have said current is entering the dots or leaving the dot. In that case, it will be mutual inductance will be positive. Here it's saying that if one current is entering and other current is leaving, or one current is leaving, other current is entering. In that case, mutual inductance will be negative.